Okay, looks like it's recording, so let's get started. So we're going to go through those test type questions that are posted on the WhatsApp group. Okay, so the first one is a thermodynamic cycle. We need to treat it as either an engine or a fridge, and then calculate certain things based on that. Okay, so our PV diagram looked like the following. So we have P and V. Okay, and then we had the points A that was given by 1, 4, B that was given by 2, 4, C that was given by 2, 1. Okay, and it was going around like this. Okay, so that's our thermodynamic cycle. The first thing we want to do is calculate the total heat added to the system. So to do that, let's just go along each of the sides of this triangle and see if heat is added or removed. Okay, so if we look at the path AB, then we can use our first law of thermodynamics to calculate the heat transferred. So delta U is equal to Q minus W. So delta U is the change in internal energy between the endpoints. So we can write that as 3/2, 2 times 4 minus 1 times 4 is equal to Q minus W. Since this is an isobaric process, that's pretty easy to calculate. That's just going to be 4 times 2 minus 1. Okay, and you can simplify that, and we end up with Q is equal to plus 10 joules. Okay, so along process AB, Q is positive, and so it's added to the system. Okay, what about BC? Let's have a look at that. So again, delta U is equal to Q minus W, but we see immediately BC is isochoric, so the work done is 0, so we can just get rid of that term. So whatever the change in internal energy is, that's the amount of heat transferred. Okay, so let's see what that is. So Q is going to be 3/2, 2 times 1 minus 2 times 4. So Q is equal to minus 9 joules. Okay, so it's negative, which means that is being removed from the system. Okay, or it's the exhaust from the engine cycle. Okay, and then the last one is from C to A. So let's see what happens there. Again, delta U is equal to Q minus W. Okay, so delta U, that's going from C to A. So that's going to be 3/2. 4 times 1 minus 2 times 1 is equal to Q minus W. That's going to be the area underneath that line because it's the integral of P dV. So if we just highlight that here, integral P dV, that's going to be this area underneath here. Okay, so we can work that out because we know the base is going to be 1 unit. So the far right end is 2, the left end is 1, so this is 1. Okay, the bottom little rectangle bit that has a height of 1, and this top bit for the triangle, that's going to be 4 minus 1, so that's going to be 3. Okay, so the area over there is going to be half base times height for the triangle part. So that's 3/2. And for the rectangle part underneath, that's going to be 1 times 1. Okay, so if we go back here, the work done is the area of that triangle part minus the area of the rectangle part. If you want to color code it, we can put this triangle part here in blue. Okay, so it's got a base of 1, a height of 3, and then this rectangle part here, that's got a base of 1 because of the 2 minus 1, and a height of 1. Okay, so that's going to be 3 over 2. We can simplify that as well. So 4 minus 2, that's going to be 2 times 3 over 2, that's just 3. Q minus area of the triangle, remember half base times height, so that's 3 over 2. And area of the rectangle, that's 1 by 1, so it's just 1. Okay, so Q is equal to 3 plus 3 over 2 plus 1. So Q is equal to, we can write that as 6 over 2 plus 3 over 2 plus 2 over 2. So 6, 7, 8, 9, 10, 11 over 2 joules. Okay, and that's positive. So we are adding heat to the system along process CA. Okay, so if we want to work out the total amount of Q added, that's going to be this 10 joules that we added for process AB and 11 over 2 joules for process CA. So that's going to be 10 plus 11 over 2. Okay, so it's going to be 31 over 2 joules. You can put a plus there because that's what we're adding. Okay, the second question asked for W net, the net work done. So if we look at this picture again, just remove this here. And draw that back. Okay, so the net work done is going to be this area within the cycle. Okay, because it's the closed loop integral going around. Okay, so again, this triangle here, it has a height of 4 minus 1, so it has a height of 3, and it has a base of 2 minus 1, so that's 1. So the net work is going to be half base times height, so that's 3 over 2. So W net is 3 over 2 joules. Okay, so we want to then work out the efficiency. So that's the eta is going to be W net over Q in. Okay, we can drop the absolute values because we're dealing with positive numbers. So W net, that was 3 over 2. Q in was 31 over 2. So that's 3 over 31. You can leave it as a fraction. You don't have to write it as a decimal. Okay, so that's the efficiency. And the next question was, is this a refrigerator or an engine? It is an engine because it outputs some amount of work. If W net was negative, that means you have to put in the work, for it to do something. Okay, but yeah, it's producing work, so it must be an engine. Okay, any questions on this first part?
So this is an engine.
Sorry, can't hear you.
Never hear your last part. Is this? You said it's an engine.
Yeah, yeah.
Because the W net is positive.
Yeah, so it's producing work, so it must be an engine.
Okay, thank you, sir.
Okay. So remember the difference between engines and heat pumps. Engines, you put in some heat and then it does some work. For a, so it's like the heat engine. For a heat pump, you have to put in some work and then it transfers the heat. Okay, so it goes backwards. So in that case, the work done by the system would be negative, meaning you put in that work. But yeah, it's positive, so it's an engine. Okay, let's have a look at the next question. And that was on the Maxwell's relations. Okay, so we start off with the definition of enthalpy. So H is U plus PV, and we want to prove the Maxwell relation involving the enthalpy. So first we need to take the differential. So dH is du plus, and then you can use the product rule here. So it's going to be P dV plus V dP. Okay, so du plus P dV, we can use our thermodynamic relation to rewrite that. So remember TdS is du plus P dV. So dH is equal to TdS plus V dP. And that's one way of writing dH. We can also write it another way, as dH is partial derivative of h with respect to s, ds, plus partial derivative of h with respect to p, dp. Now, this is just two ways of writing the same thing, so we can compare the terms. So dH by ds is equal to t, and dH by dP is equal to v. Okay, good. Now we can do the mixed derivatives. So for the first one, we're first differentiating by s, so let's differentiate by p now. So d by dp of t, that must be equal to this dH by dP, but differentiating by s, and the other variable, so that we get the mixed derivative. So that must be d by ds of v. Okay, and we can write this in the form that the question had. So this is going to be dt by dp, keeping s constants. Okay, and this must be equal to dv by ds, and then keeping p constant. Of course, that's the other variable for the other side. Okay, so it's always going to be something like this with the d by dp, and on the other side you keep the p constant, on that side you keep the s constant, and here you differentiate by s. Okay, because remember we swap the derivatives to get the mixed derivatives, and then that gives us our Maxwell relation. Okay, so here we used the enthalpy H to get this Maxwell relation, but of course you could use the other thermodynamic relations, the other thermodynamic potentials, and that will give you the other Maxwell relations. Okay, but the process is exactly the same. You take the differential, you compare it to the total differential, match up the terms, take the mixed derivatives, and then that gives you your Maxwell relation. Okay, any questions on this? Yeah, not so bad. Let's have a look at the next one. Okay, so here we're given the entropy, and we want to calculate the pressure and the internal energy. Okay, so S is equal to NKB, and then we have brackets, natural log of NQ times V minus NB all over N. Okay, so that's all inside the natural log, and then plus 5 over 2. Okay, so that's our entropy, and NQ, that's another term here. This is just a function of temperature. So that's going to be given by 2 pi m kb over h squared times T to the 3/2. Okay, so it only depends on temperature. The rest are constants there. Okay, so notice that this entropy depends on volume, number of particles, and temperature. However, normally entropy would depend on the internal energy, U. Okay, so we don't have the expression for U here, so it's a bit different to the standard variables for entropy. Okay, just to point that out. Okay, so the first thing we want to do is calculate the pressure. Okay, so there's a number of ways to do that. So you can find the free energy and then find the pressure from that, or you can use one of Maxwell's relations. Okay, let's use one of Maxwell's relations. Okay, so we've got entropy, we want to find pressure, so you just look through the relations until you find the one involving those two. Okay, so that's going to be ds dv at constant temperature T is equal to dp dt at constant volume V. Okay, so that's one of Maxwell's relations. You should have derived this in the last hand-in problem. Okay, so they're pretty good to remember because it's useful in cases like this where you're given the entropy, you want to calculate the pressure, this relates the two. Okay, on the left-hand side, we take the derivative with respect to volume. So this is going to be d by dv of the entropy. So that's nkb, natural log of nq v minus nb over n plus 5/2. Bracket there, and bracket there. Okay, so that's on the left-hand side, and then on the right-hand side, we have dp dt at constant volume V. Okay, so let's take the derivative with respect to volume. So that's pretty easy. The volume only appears in the log term. So this is going to be nkb divided by V minus nb. And this is equal to dp dt at constant volume V. Okay, now we want to find the pressure. So we need to integrate both sides with respect to T, and that will undo the derivative there. So P is going to be equal to the integral of nkb over V minus nb dt plus some function of V, since when we took that partial derivative, V was fixed. So when we undo the partial derivative, we need to add this function back. Okay, so we don't know what the function is, but it's some function of V only. Okay, so this gives us P is equal to nkbt over V minus nb plus some function of V. We don't know what that is. However, if you remember from, I think it was hand-in problem 4, I think it was, this function, we found what that was. This is equal to minus an squared over V squared. Okay, and then that gives us our pressure here. Okay, any questions on this? Okay, the next thing to find is the internal energy. Okay, so let's have a look at that. Okay, so let's just rewrite that entropy again. We're going to need it. So, S was nkb natural log of nq v minus nb over n plus 5/2. Okay, so we've got the entropy. We want to now find the internal energy. Now, again, there's a number of ways of doing this. I don't mind which way you do. Okay, so that's up to you. So we want something that includes the internal energy and something that includes the entropy, because that's given. Entropy is given. We want to find the internal energy. The first thing that comes to my mind is the free energy. So the free energy F is given by U minus Ts. We know what S is, that's given. U we want to find. Okay, so this gives us some relationship between the two. And we can use that to find U, provided we can find F. Okay, but that's not too bad. We can find F using the fact that the entropy S is minus dF dt if we hold V constant. So we can use this differential equation here to find F. Once we have F, we can substitute it into the above equation and then find U. Okay, so let's do that. So minus dF dt as a function, keeping V constant is equal to the entropy, but we know the entropy there. That's going to be NKB. NKB, the natural log of NQ. I'm just going to split this up. Plus NKB, the natural log of V minus NB over N, plus 5/2 NKB. Okay, so that is the entropy there. Now, what we can do is integrate this with respect to T, and that will undo the derivative and then give us F. Okay, so let's just put the minus on the other side first. So we have dF by dt, holding V constant, is minus NKB, natural log of NQ, minus NKB, natural log of V minus NB over N, minus 5/2 NKB. Okay, good. Let's now integrate with respect to T. So F is going to be equal to minus NKB integral of the natural log of N, subscript Q, dt, minus NKB. We can just put the T there now because that's not a function of T. Natural log of V minus NB over N. And same for the other one, we can just add the T immediately. We don't have to worry about the integral signs. Minus 5/2 NKBT. And remember, we held V constant. So when we took the derivative with respect to T, we lost any function of V. So plus some function of V, we don't know what it is yet. Okay, so most of it's done. We just need to worry about this bit over here, and that's integrating the natural log of NQ. Okay, so remember what NQ was. NQ was given by 2 pi m kbt over h squared, all of that to the 3/2. Okay, so what we can do is split this up because we're only interested in the t term. So if we write this natural log of NQ, we can write this as 3/2 natural log of 2 pi mkb over h squared plus 3/2 natural log of t. Okay, because we're only interested in the t part. We're not too worried about the constants in front of it. So if we do that, we can integrate everything nicely. So just integrate that part nicely. So F is going to be minus NKB. And then we're going to have 3 over 2 T natural log of 2 pi mkb over h squared plus 3 over 2 T ln T minus T, brackets there. Okay, and then we have all the other terms. So minus NKBT, natural log of V minus NB over N, minus 5 over 2 NKBT plus F of V. Okay, so that is the free energy for the system. Okay, now that we've got that, we can use our relation here. F is equal to U minus TS to solve for U. So U is going to be F plus TS. So U is going to be F plus TS. So this is going to be the free energy. We just worked that out here. So that's going to be minus 3 over 2 NKBT, natural log of 2 pi mkb over h squared, minus 3 over 2 NKBT, natural log of t, plus 3 over 2 NKBT minus NKBT, the natural log of V minus NB over N, minus 5 over 2 NKBT, plus our function F of V. We still don't know what that is. Okay, so that's the free energy part. Now we need to add T times the entropy. So it's going to be plus T times the entropy. We had that above. That was NKB, natural log of NQ, and all of that. So let's write that. So T times NKB in brackets, natural log of NQ. Let's just put it separately there. Then it's the natural log of V minus NB over N, plus the natural log V minus NB over N, plus 5 over 2. Okay, and then a lot of things are going to cancel. So this first part here, minus 3 over 2 times T, natural log of that. This and this is going to go. That and that's going to go. The 5 over 2 and that's going to go. And then that's going to go as well. So these two together, they're going to cancel with that. Okay, so we're left with 3 over 2 NKBT and this function of V. So U is equal to 3 over 2 NKBT plus this function of V. Okay, and again, if you remember from hand-in problem 4, I think it was, this function of V, that was minus AN over V. Okay, but you don't have to worry about that here. Okay, so just given this entropy, here, if you do the calculations, this function of V is undetermined. Okay, but if I give you the total free energy, then it includes this term over here. Okay, but just with what we're given, this is going to be the final answer.
In the test, if we don't write, if we write the U is equal to 3 NKBT plus F of V, but we don't write that minus AN over V, we will get marked down.
Yeah, so this minus AN over V, that is an extra term from the free energy. So you see here, this entropy doesn't have that. It's got our, this term here, sorry, it's got this term here, but it doesn't have that other term. So if you remember with the van der Waals gas that you did in the homework problem, remember it was P plus AN over V squared times V minus NV is equal to NKBT. So you found this. You see this extra term here is in the equation of state, but it's not in the entropy. So that's why we couldn't find it here. Okay, so if I give you the entropy and I ask you to find the pressure and the internal energy, you can just leave it like this, that's fine. However, if I give you the free energy and I ask you to calculate the other stuff, then it will include this term.
Okay.
Yeah, so it depends on what I give you. Okay, but either way, you should know that that function exists. Okay, because if you just look at with the partial derivative, here we took the partial derivative with respect to t. So when we integrate t, we have to get that function of v back anyway. So it should be there in either case. Okay, is that all right?
Yes, sir. Thanks.
Okay. And then the last question was on the Boltzmann distribution, finding the most probable velocity. So let's have a look at that. Okay, so we're given, f of v is equal to m over 2 kBt to the 3 over 2, 4 pi v squared. And then we have the exponential of minus mv squared over 2 kBt. Okay, and in the last lecture, I showed you what this looks like. Okay, for some fixed mass and temperature, it's going to be something, it's going to be something like that. Okay, some function like that. We want to find the most probable velocity. So at fixed mass and temperature, that's going to be where the gradient is 0. In other words, here where we have a maximum probability. And that gives us our most probable velocity there. Okay, so we need to take f differentiated by v, set it equal to 0, and solve for v. That will give us our f prime of v is equal to 0. Yeah, that's what we want. We want to solve for this v here. Okay, so let's do that. F prime of v is going to be equal to this constant in front. It's not going to do anything when we set this to 0. So let's just take it out to the front here. M over 2 pi kBt to the 3 over 2. And now we can do the derivative. And the 4 pi we can take out as well. That's not going to do anything here. Okay, so differentiating v squared is going to be 2v. And then we have the exponential of minus mv squared over 2 kBt plus v squared exponential of minus mv squared over 2 kBt times minus mv over 2 kb, sorry, not the 2 goes away, over kBt. And close the square brackets. Okay, so we've got the derivative. This must be equal to 0. Okay, so that's why I took all the constants out to the front, because if all of this is equal to 0, then we don't worry about any of those constants there. Next, the exponential is common to both terms, so let's take that out to the front. So we have the exponential of minus mv squared over 2 kBt And then the leftovers is going to be 2v plus v squared, and then we have minus mv over kbt equals 0. Okay, and we also have another factor of v that we can take out. So there and there, let's take that out to the front. Okay, so this exponential term, that's never going to be 0, so we can get rid of that. And we're not interested in 0 velocities, so all of that can go. So we're left with 2 minus mv squared over kbt is equal to 0. So mv squared over kbt is equal to 2. And so v is equal to the square root of 2 kbt over m. Okay, so that is our most probable velocity. So if you've got yourself a box of non-interacting ideal gas particles and they're moving around at some temperature T with mass m, then this is the most probable velocity that you're going to find. Yeah, of course, you're going to find all the velocities in the distribution with the respective probabilities, but this one has the highest probability. Okay, any questions on this one?
The question previous to this, so when we're doing like in a test, so we just look at which Maxwell, which one relates to which.
Sorry, can't hear you. Please repeat that.
For the question previous to this, we did the one we given S and then we use the Maxwell's relation. So
previous question here, yeah.
So when we're doing it actually in the test, so we just look at what relates to what.
Yeah. So if we look over here, the question asked us to find the pressure, and we're given the entropy. So you can use the Maxwell relation to find that, like I did here. But that's not the only way. There's a number of ways to do this. Or if you forget the Maxwell relation, you could just say, well, I know TdS is equal to du plus pdv. Okay, I know that. So ds is equal to 1 over t du plus p over t dv. Okay. I also know that ds is going to be ds by du du, which is ds by dv dv. Okay. I know that just from taking the total differential. So if I compare the terms there, I know ds dv is equal to p over t, which means that p is equal to t ds dv. You could do this as well. You'll get exactly the same answer. So again, there's a number of ways of doing it. You do whatever you feel like you're most comfortable with. So if you remember the Maxwell relations and you want to do it that way, that's fine. If you want to find the differentials and do it that way, you can do that as well. Okay, both are perfectly fine.
Okay, so.
Okay, just remember with this way, this is holding U constant. Okay, however, this entropy here, this doesn't have U. Okay, U isn't specified. So just be careful with that. Okay, because remember S, the natural variables for S are U and V. Here we're given it in terms of V and T. So here is V and T. Okay, so just be careful which variables you're actually working with. Okay. Any other questions? Okay. Any questions about the test?
What time will the test be, sir?
I think I already put that on the group. It's during the tutorial period on the Tuesday, so from 10:30. Okay. Then you've got an hour to write the test, and then 45 minutes to submit the test. So then that should cover the full double period that we have on the Tuesday.
Yes, sir.
Okay. Anything
Brandon.
else? Yeah.
Just asking, will the test be hard or? I'm just wondering.
Well, if you studied, it should be easy. If you didn't study,
Mhm.
it's going to be hard.
Okay.
It's
That's
not
right.
that. So,
Uh,
so the first part of the test is engines and refrigerators. You know, the usual stuff that we've gone over, like
yeah,
the stuff.
yeah.
That's the first part. The middle part is on thermodynamic potentials. So this stuff, yeah.
Okay.
You know,
Okay.
the free energy, the enthalpy, all of that stuff. And then the last
Yeah.
part is on the Boltzmann distribution. So
Oh.
something like this.
The last part is for like we said it's 10 marks.
I think no, it's 13. There's a couple extra marks for there's a little extra bit that you do at the end. So that's another 3 marks. But the most of it is 10. So like the main question is 10, and there's a little calculation bit at the end for another 3 bonus marks. So the last bit's out of 13. Okay. Any other questions?
Not really, sir. Thank you.
Okay, cool. Is there anything that you want to go over on Monday? Because we do have that time on Monday as well.
So maybe you can just send us a question on WhatsApp involving the Maxwell, the previous one you did before. Then we can do it, and then we can just go over the solution on Monday.
Which one?
The previous, yeah, same one.
Yeah.
You can maybe give us another question like on this, and then we can do it, and then we can show you and then we can give you the solution on Monday, our one.
Okay. Yeah, sure. We can do that. Yeah, I can come up with another one for you to try.
And like finding pressure or whatever, and then on Monday we can just go over through that.
Yeah, sure. We can do that.
Thank you, sir.
Okay. So I'll come up with something now, and then I'll just post it on the WhatsApp group, and then you can have a look. Oh, and remember that the last hand-in problem plus the assignment is also due next week. Okay, so that assignment will count as like a bonus hand-in problem, if you want to think about it like that. Okay, and then at the end of the week, I can give you your mark for the first part of the module. And then that will give you an idea of what you're working with for the second part. Okay, and then just on that, the second part of the module, it will be the same kind of structure. So you'll have your 2 tests for the first bit and the second bit of work, and then you will also have hand-in problems as well. Okay, so the structure is the same. And then everything just gets added together for your total semester mark. Okay, So in a few minutes, I'll send that problem on the WhatsApp group, and then we can go through it on Monday. Okay, and I think the recording also works. So I'll upload this to YouTube, and you can go over it again. Okay, bye everyone. I'll see you Monday.